So when we started talking about inductors last Friday, we really only introduced two different possibilities, both of which were a coil wrapped around a core. For capacitors, there are a lot more different geometric configurations that they can take. So we are going to focus our efforts on the most common and the most classical, which is the parallel plate capacitor. So in a parallel plate capacitor, we have a pretty simple configuration. We have a plate up here on the top. And another plate down here on the bottom, connected to a set of terminals. So this is our top plate. This is our bottom plate. And there is usually, but not always, a medium in the middle called a dielectric. Now, this dielectric material, depending on the type of capacitor, could be air, could be vacuum, so actually nothing, could be ceramic materials. Effectively, it just needs to be some sort of insulating material so that current cannot flow easily from the top plate to the bottom plate. Okay, so this is the basic configuration for our capacitor, and I'm going to give you guys some figures of merit here. Let's call this dimension the length, this dimension the width, and then this dimension right here is the distance between the plates. And the area of the plates and the distance between the plates are hugely important to a device's capacitance. Now, when I walked in the room, there was a question about what capacitors are made of. Capacitance occurs anytime there are two conductive materials near each other that don't have a conductive path between them. Full stop, okay? Doesn't matter if it's two chunks of semiconductor material or metal plates or some combination thereof. If it is two conductors next to each other, so even a pair of wires that aren't connected exhibit some capacitance, but it'll typically be pretty small because the area of overlap between those two conductors is small, okay? So in our class, what the capacitors are made of, what the dielectric material and all that kind of stuff is, don't really play a large role in how these guys behave. In your physics classes and your E&M classes and all that kind of stuff, when you go further in electrical engineering, that's absolutely hugely important. But for us here in a low-level circuits class, we're just trying to figure out how this thing does what it does, okay? So capacitors are used in circuits as a form of temporary energy storage. So they are used in a similar fashion as an inductor, but I don't want to say that they are interchangeable, although their roles are very, very similar, okay? So how an inductor stores energy is by concentrating that magnetic flux, all right? How a capacitor stores energy is by physically moving charge onto the plates, right? So if we were to apply a voltage across a capacitor, what we would see, let's say that we put a positive polarity terminal up here and a negative polarity terminal down here. I don't know why that looks like a C right there. I don't remember what that's supposed to be. Okay. Effectively, what would happen is that electrons would move towards the positive polarity terminal voltage, leaving behind positive charge on this top plate, right? Plus Q. And that positive charge on the top plate attracts negative charge to the bottom plate. And for every single positive charge that we have on the top plate, we attract a corresponding negative charge, so that our system is always electrically neutral. All right. So we are going to be talking about current voltage relationships for this guy in just a couple of minutes. And so a very good question that you might ask is, how the heck can there be a current flowing through this thing when there is, by definition, no path for conduction to occur, right? These are two plates that are physically separated from each other. Well, the action of moving charge onto the plate is causing a current to flow. And so what I mean by that is it's not a conventional current that we think of, but for every positive charge we put on there, when we moved the charge there, current was flowing because charge was moving. Similarly, when we discharge this capacitor and allow the positive charge to move off the top plate and the negative charge to move off the bottom plate, we see that current flows as well, right? So moving the charge onto and off of the plates causes what's called a displacement current. That displacement current means absolutely nothing to you guys. It's just a different mechanism for current to flow. It behaves in the exact same way as the conventional current that we've been discussing. And because this is a low-level circuits class, we're going to treat it in the exact same way, okay? So charge doesn't pass through the dielectric material. Charge just moves on and off the plates. And that's where our current voltage relationships are going to come from. All right. So charge separation across the capacitor's plates results in a difference of electric potential or voltage as charge, that does not look like a G, Q will be equal to capacitance C multiplied by voltage V. So from this, capacitance can be defined as the ratio in the change. I don't know why I can't write G's today. In electric charge of an element due to a corresponding change in electric potential. Or C is simply charge over volts. Unit-wise, that looks like coulombs per volt, which is an amp second per volt, or more commonly called 1 farad. Because 1 coulomb of charge is so massive. 1 coulomb of charge requires almost a billion electrons. That's just Q. Let me write that less crappily. So the ability of a capacitor to store charge is governed by 2 factors. All right. So for our parallel plate capacitor up here, we could say that this capacitance C is equal to epsilon W times L over D, where W, L, and D are geometric quantities relating to the size of the capacitor. So W and L gives us the area of the plates. D is the physical separation between the 2 plates. And epsilon there is what's called the permittivity. Okay? Permittivity is a material property. All right. So the permittivity tells us effectively how well that material there that I've outlined in red, that dielectric, acts as compared to a vacuum. All right. So air is like 1.001 times as good of a vacuum. So they're effectively the exact same thing. All right. Undoped silicon has a relative permittivity of 11.6, which means it's 11.6 times as good of a vacuum. Deionized water, so water where all of the minerals have been stripped out of it, so it's just purely hydrogen and oxygen, is actually 81 times better than a vacuum. It's one of the best insulating materials on the planet. The only problem is water doesn't particularly like to stay deionized, and as soon as impurities get there, that thing drops significantly. Okay. So let's talk about circuit characteristics. Bless you. The schematic symbol for a capacitor, there's actually 2 of them. We are only going to deal with one in this class, but you may see the others or may have seen the others, the other one as well. So for our generic capacitor, C, we have 2 parallel plates. So its schematic symbol also actually looks like what it's physically representing, right? For an inductor, the schematic symbol was a coil of wire because it was made of a coil of wire. Here, our schematic symbol for a capacitor is a conductive path, a wire, that's broken up by a pair of parallel plates. It obeys the passive sign convention. So if we have a current IC of T flowing through the capacitor, and by through, I mean, I'm talking about that displacement current, and that current is flowing into the positive polarity terminal of the capacitor, generating some voltage, VC of T, then the capacitor is absorbing power. If the current were flowing into the negative polarity terminal, it would be supplying power. Since this is an energy storage element, the capacitor can absolutely actually supply power. So it does not convert energy into heat like a resistor. All right. Our second schematic diagram or schematic representation for a capacitor is this guy right here, where we have one straight plate and one curved plate. This guy also obeys the passive sign convention. And this is what's known as an electrolytic or polarized capacitor. So the difference between these two things is pretty simple. If you plug up an electrolytic capacitor wrong, meaning that you apply a higher potential to its negative polarity side than you do on its positive polarity terminal, it bursts, physically breaks. So if you ever crack open a computer or something like that, and you look at the big capacitors in there, they're usually cylindrical looking circuit components with a little metal plate on the top. If you ever see that the plate has curved up or something like that, that's an electrolytic capacitor that is burst. Okay, so it doesn't actually release any fluid or anything like that unless you were to physically break open the canister. But applying that wrong polarity voltage causes a physical deformation in the structure, which causes it to no longer act as a capacitor, and you have to replace it. Yes, C is just capacitance. Yes. All right. So some textbooks use these schematic symbols interchangeably, okay? But in a real technical drawing, the curved plate one actually means an electrolytic or polarized capacitor. None of the capacitors that we are going to physically be dealing with in this class or theoretically be dealing with in any of our circuit analysis will fall under that condition. So we're just you're gonna see that top one for everything that I do as far as your tests and all your experiments and all that kind of good stuff. I just want to make you aware that if you're studying from other things or watching YouTube videos from somebody else, you might see this other symbol as well. And so I wanted to tell you what it meant. All right. So we know that electrical current, by definition, is the derivative of charge with respect to time. All I'm doing right now is including that subscript C for current and charge because we're talking about a capacitor, but this is the exact same relationship that we talked about on our second day of class. Current is a derivative of charge with respect to time. And we know that there is a relationship between charge and voltage for a capacitor. And so what this gives us is C dV by dt. So this is our first relationship, current voltage relationship for a capacitor, okay? The current is simply the capacitor value multiplied by the derivative of the voltage. So there's three things that I want to talk about for this relationship, all right? The first one is, does this equation look familiar? Let's start there. Yes, it looks like the voltage equation for an inductor. In fact, if you replace I and V and L and C, you will find that all of the relationships that we derived on Friday are going to show up again today. Literally, every single one of them is going to show up again where the voltage and current are switched, and we replace all of our L's for inductance with C for capacitance. They are that closely related. They're called electrical duals, okay? So they have the exact same characteristics, except that the current voltage, current and voltage are interchanged. So with that out of the way, we can glean two observations regarding the behavior of a capacitor from this equation, just like we gleaned two pieces of information regarding the behavior of the inductor from its equivalent equation, right? So in a DC circuit, where the voltage drop across the capacitor does not change as a function of time, what must the current flowing through the inductor be? 0, okay? So that means that in a DC circuit, a capacitor behaves like an open circuit, right? Because the current flowing through it must be 0. The second relationship we will arrive to at the exact same way. What happens if the voltage drop across the capacitor is discontinuous, right? Meaning that we have a voltage, like this. Let's say that we have V of t, here's t, and let's say that our voltage is a constant value and then abruptly drops down to 0. What would our current look like? Let's call this at some time, Any thoughts? What's the derivative of that voltage expression when it changes? Infinitely large, right? So that means that for a capacitor voltage to change abruptly, it would generate an infinite amount of current, which obviously cannot happen because that would be in violation of the law of conservation of charge, right? We cannot generate or destroy an infinite amount of current in an infinitesimal amount of time. So graphically, this would look like an impulse function, like so, but generally speaking, it's bad. So we can say that the voltage drop across a capacitor cannot change abruptly. So just to try to burn this into your heads, because it's going to become critically important as we are talking about transient analysis for the next week, starting on Wednesday. The current through an inductor cannot change abruptly, and the voltage across a capacitor cannot change abruptly. We are going to use these two simple sentences to form the basis for how we treat our energy storage elements when we shift away from DC steady state, which is all the transient analysis that we're going to be talking about means. Okay. So statement 2 here and statement 2 for inductors, extraordinarily important. So much so that you will directly and indirectly be tested on these 2 statements multiple times on your next test. So this will pretty much 100% show up as one of the theory questions, and it will also be used practically in your analysis multiple times on exam 2. So learn it, or in a worst case scenario, simply memorize it, but I'm just letting you know how critically important it is for you to understand the second relationship here. All right, so equation 1 that I boxed in red lets us know what the inductor current is based on the behavior of the voltage signal. So let's slightly rearrange that relationship, and we find that the voltage drop over a capacitor, VC of t, is equal to the integral from -infinity to t of our, excuse me, I've left off something here that's very important. 1 divided by C multiplied by the integral of the capacitor current as a function of time. And we can further rewrite this guy as the integral from some time t naught, where we know what the capacitor voltage is, to some later point in time t of IC of x dx plus VC at t naught. So this is equation 2. And this guy shows us that capacitors also have memory, right? Meaning that their behavior in the present depends on how much voltage appeared across its terminals in the past, right? Exact same relationship as we saw with inductors on Friday, but the V's and I's are switched, and now instead of L, we have C, right? The power absorbed by a capacitor is always the product of the capacitor current and the capacitor voltage. And so we can express this as C VC dV by dt. And we can say that the energy absorbed by our capacitor is the integral from -infinity to some later point in time of the power absorbed by our capacitor as a function of time. And substituting in our previously derived relationship, this is going to be the integral of C V, sorry, D dt, which looks like integral from our capacitor voltage at -infinity to our capacitor voltage at present time t of C dC dVc. And if we take the voltage at time t is equal to -infinity to be 0 volts, this reduces to 1/2 C times the voltage squared. So here we have relationship number 4. All right. So before we move along to how we can combine capacitances, I want to take a moment. Okay. As I believe I have said previously, the amount of material that is on your next exam is not a whole heck of a lot. There is Thevenin and Norton equivalent circuits, capacitance and inductance, and then transient analysis. Really only 3 topics. Now, I absolutely understand that those 3 topics take us 7 lectures to get through, but it's only 3 topics. The only equations that you need to learn or memorize are these 4 that we've discussed today and the 4 that we covered on Friday. People have asked if there will be an equation sheet on the exam. The answer is no. So I'm letting you know right now to start drilling these into your head, okay? Particularly the current voltage relationships, right? The power relationships are fairly straightforward because it's just a product of current and voltage. The energy relationship, I would say you need to really memorize that one too, just because it's not as obvious as the power relationship. But if you understand what this concept of electrical duals that I've talked about means, you really only need to know one set of the equations because you can instantly get the other set by just replacing I and V and change all your L's to C's or vice versa, right? They are literally the exact same relationships, 100% of the way. So in truth, you can get by memorizing just 4 and understanding what the concept of an electrical dual means. All right. So let's talk about combining capacitors. Oops. Combining capacitors. So let's say that we have a network that contains multiple capacitors connected in series. So let's call this guy C1. Actually, let's put that up top. This guy C2. All the way out to some capacitance C sub n. Like so. And there is some total voltage VT across all of these capacitors in series. And there is some current I of t flowing through them. I can express the voltage drop over each of my capacitors as V1 of t, and then the voltage drop over capacitor C2 will be V2 of t, and so forth, until I get here to Vn of t. And I can apply Kirchhoff's voltage law and say that Vt is equal to V1 plus V2 all the way out to V sub n. And I can express all of these voltage drops in terms of my common current flowing through all of the elements here in this series connection. So that would look like 1 over C1 times the integral from negative infinity to t of I of x dx plus 1 over c2 times that same integral all the way out to 1 over c sub n multiplied by that exact same integral, bless you. And then I can say then that my voltage V of t is 1 over C1 plus 1 over C2 plus 1 over C sub n integral from negative infinity to t of I of x dx, which is equal to 1 over the equivalent capacitance integral from negative infinity to t of I of x dx. And so from this, I can see that my equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C sub n. So all of this fancy pants math that I have done here, what does it mean? Capacitors in parallel, capacitors in series combine like resistors in parallel, okay? And without derivation, although it's pretty easy to see what's going to happen, if we had a network containing a bunch of capacitors connected in parallel, we applied Kirchhoff's current law to that network, we would find that capacitors in parallel combine like resistors in series. All right, now I have an in-class assignment here that I absolutely want you guys to work on and all that kind of good stuff. But before we do that, there are going to be a couple of homework problems that you guys get where you'll have circuits that contain both capacitors and inductors. And so I want to work with you on a couple of problems of that nature so that we can really see what's going on. All right. So my in-class assignment is all strictly dealing with capacitors, but I want to kind of get you over some of those hurdles that you might see. So the first problem that I want to work, let me move this over here, is this guy. Let's say that we have the following circuit where we have a 5 ohm resistor like so, 30 volt source, a 6 ohm resistor like so, a 6 millihenry inductor, a 20 millifarad capacitor, a 4 ohm resistor, and 10 ohm resistor out here, a 2 Henry inductor here. Sorry, let's call this, instead of millihenries, full henries, so that the units are the same. And over here, we have a 10 millifarad capacitor. I'm going to call this guy C1, this guy L1, this guy C2, and this guy L2. All right. I want to know the energy absorbed by capacitor C1 and, let's say, the energy absorbed by inductor L2. Anybody have the foggiest clue how we could go about figuring out either of those things? Let's start there. Anybody have a thought?
The voltage isn't time varying, is it?
That's correct. The voltage is not time varying.
And wouldn't the inductor be a short circuit and the capacitor acting as a circuit?
Absolutely correct. So with this DC circuit, and we can tell that it is a DC circuit because our independent source here is a DC quantity, means that we can treat all of our inductors as short circuits and all of our capacitors as open circuits, right? So we could redraw this guy, and I'll do it kind of quick here. Let's see. We have a resistor, 30-volt source, resistor, like so. All right, so this is 30 volts, 5 ohms, 10 ohms, 6 ohms, and 4 ohms. So my circuit is redrawn. How does that help me? So let me ask a slightly different question, okay? I'm going to scroll back up here for a moment. If I want to know the energy, Drew. Oh, sorry, thank you. Yep. If I want to determine the energy stored by a capacitor, what quantity do I need to know? The voltage drop across the capacitor, right? So since I'm trying to find the energy stored by capacitor C1, I'm going to call this voltage VC1, all right? Where I just arbitrarily chose that polarity, and because I know that the energy stored by a capacitor depends on the voltage squared, the polarity that I choose doesn't matter even a little bit. Everybody okay with that? Sure, so the energy stored by a capacitor is 1/2 CV squared. Since the voltage is squared, the polarity that we choose doesn't influence our energy stored at all. If I want to find the energy stored by an inductor, what quantity do I need to know? The current flowing through the inductor, all right? Since we're trying to find the current, the energy stored by inductor L2, I would say that this current is IL2, right? Where the direction that I choose is again entirely arbitrary. Doesn't influence our behavior of our inductor in any way, shape, or form. So for our redrawn circuit, where should that capacitor voltage and where should that inductor current be? Same exact place, right? So the current flowing through my 6 ohm resistor represents the current flowing through my inductor L2 because those two elements were connected together in series. Everybody okay with that? Similarly, this voltage drop here across this set of open circuit terminals will be my voltage VC1. Everybody okay with that? So how could I determine either of these two quantities?
That's pretty easy. It's a single path. There's only one photo blue.
Okay.
You can combine those in series to Ohm's Law. Very quickly get that.
Okay. So both of those methodologies are absolutely what I would go with here. So what Ian has suggested is that the current that leaves my 30 volt source is going to flow up and pass through the 5 ohm resistor. None of it can continue going up because it sees an open circuit. None of it can veer off to the left because it sees an open circuit. So all of that current continues going to the right. When it reaches here, none of it can flow up because it sees the open circuit. So all of it flows down, turns around like so. None of it can continue flowing to the left. So all of it must flow up like that. So by using nothing more than good old Ohm's law, we can say that that current IL2 is simply 30 volts divided by just all of the resistances that that current I've drawn in blue passes through, which would be 5 ohms plus 6 ohms plus 4 ohms. So 30 volts over 15 ohms gives me 2 amps. And from here, the energy stored by this inductor is going to be 1/2 times 6 henries times 2 amps squared is going to look like 12 joules. Anybody have any questions, comments, concerns about that portion? What Cheston has suggested is that we can now write a Kirchhoff's voltage law equation around that left-hand path that contains the open circuit over which we're trying to determine our voltage, right? So I'm going to draw that path in pink. And so let's start here and just follow it around like so. So let's start down here. And so we can see that we'll have negative 30 volts plus 5 ohms times, well, what's the current flowing through that 5 ohm resistor? 2 amps, we just found it, right? Now we see the 10 ohm resistor. What's the current flowing through the 10 ohm resistor? 0 amps, right? Because it's not part of a closed current carrying path. Plus this voltage VC1 is equal to 0, which means our voltage VC1 is 30 volts minus 10 volts is 20 volts. And from this, WC1 is equal to 1/2 times, let's see, C1 was 10 millifarads times 30 volts quantity squared. Excuse me, 20 volts quantity squared. I apologize. Is equal to 2 joules. Catherine. So I have negative for the voltage source.
Yeah, for the Ohms Law. Or the not.
Okay, so if we wrote our expression for IL2 and we did a Kirchhoff's voltage law loop around that right-hand loop, what we would have is negative 30 volts plus 5 IL1 plus, excuse me, IL2 plus 6 IL2 plus 4 IL2 is equal to 0. And rearranging that expression, we'd get exactly what we see up there. So I skipped that initial Kirchhoff's voltage law step and just went straight to Ohm's law because I thought we had had enough practice doing it.
Right, yeah, I understand, I understand that part, so I thought you had to do the negative.
No. Well, no, so we're doing the, okay, because we're not taking the voltage. So, okay, I understand what your question is there. Okay, so for a resistor, you're absolutely correct. If we have a resistor and the current is flowing into the negative polarity terminal of the resistor, then we do have to include a negative sign, but our source isn't a resistor, right?
Why doesn't it be negative for the left? Like 2 amps is blowing up for I2, then shouldn't it be 2 amps blowing down for I1? Because they need to counteract each other to 0.
They don't counteract each other. It's only one current. So we're not saying that there's any opposing currents here whatsoever, right? There is only one single current flowing around the loop, and it's the one that's flowing in blue. That pink expression, or the pink line, is the path around which we are writing our Kirchhoff's voltage law equation. Okay. So there is no current that circulates in an opposite direction that will cause any cancellation to occur at all, right? So the current flows in that blue loop around that right-hand side, which is how we determined IL2. And then we use the results of that expression to apply Kirchhoff's voltage law to the left-hand path, right? And the left-hand path, just to be clear, isn't a loop because it's not closed. So no current can flow through. So let me ask you guys a question. What do you feel about the difficulty of that problem? Literally straight from an old test. Yeah. Okay. Now, let me see if I have anything else meaner here. All right. Go to the next page. So let's say that we have the following circuit where we have some time varying current source. We have a 1 kilo ohm resistor, a 1/4 Henry inductor, and a 10 microfarad capacitor. our goal is to figure out this voltage Vs of t, knowing the following pieces of information. Is of t is equal to 40 e to the minus 800 t milliamps for t greater than or equal to 0, and Vc at t is equal to 0 is 5 volts, where Vc has the following polarity. And our goal is to figure out what Vs of t is for t greater than or equal to 0 seconds. All right. I would argue that this is probably one of the absolute hardest questions or close to it that I could ask you on any of our circuits tests. Okay. It is very similar to a couple of homework problems that will pop up on homework 12, which is the one that's assigned for today's lecture. Okay, so that's why I'm taking time to go out of my way to talk about it. So, does anybody have any thoughts on how we might wrap our heads around approaching something like this? So yes, at that particular point in time, the capacitor does behave as if it were just simply a 5-volt DC source, but I don't know how that helps us for this guy.
We find Vc of t using the current and the capacitance and the initial time given.
Okay, so can we find Vc of t since we know the current flowing through the capacitor and we know the initial condition on the capacitor? Absolutely. So let's start there. That's something that we can do. So Vc as a function of time is going to be 1 over c integral from t naught to t of our current Is plus our initial condition Vc at t naught. So if I substitute in the numbers that I'm given here, I will have 1 over 10 times 10 to the minus 6 farads, because that's 10 microfarads, multiplied by the integral from t is equal to 0 to some later point in time of 40 times 10 to the minus 3 amps multiplied by e to the minus 800t. Excuse me, that should actually be 800x dx plus my initial condition on this guy, which is 5 volts. So what happens? Well, let's start with something pretty easy here, right? So I can move that 40 times 10 to the minus 3 outside of my integral because it's a constant. Everybody okay with that? So 40 times 10 to the minus 3 amps divided by 10 times 10 to the minus 6 farads. Now, before we go forward from here, what is this? Anybody have any thoughts? So the 40 over the 10 is going to look like 4. 10 to the minus 3 divided by 10 to the minus 6. What's that going to look like? Four times 10 to the positive 3, right? Okay. So 4 times 10 to the positive 3. So let's get rid of this crap right here. Now, what's this amps per farad business? Seconds over volts, I disagree. So a farad is an amp second per volt, right? Volts over seconds. All right. Now I'm going to do this integration where I'm just integrating e to the negative 800x. So integral from 0 to e of e to the minus 800x dx. And then over here outside of my integral, I have plus 5 volts. So how do I do this integral? Let's start there. This is something that I expect you guys to be able to do. What did you say, Kyle? I disagree. When I take the derivative of the exponential, I move alpha. When I take the integral, it's 1 over alpha. All right. So this is going to look like 4 times 10 to the 3 volts per second multiplied by 1 over 800. Now what's important here, okay, and it's not obvious, so that's why I'm taking a moment to explain it. Our exponential function, the argument of that should be unitless, okay? So if x is a variable representing time, then 800 has to have units of per time or per second. So the units on that 800 will be per second, which winds up canceling this guy and this guy, giving us an answer entirely in volts, okay? Exactly right, per second, yes. Or hertz if you want to get weird with it. Now I will have, oh, absolutely, yeah, you're correct, Joy, thank you. Negative out here. Thank you very much, I missed that. So we're going to have e to the negative 800x here, and we need to evaluate it at t and 0. And we got to add 5 volts to it for our initial condition. So what happens when we divide 4,000 by 800? 5, all right? So we're going to have negative 5 volts. What happens when we evaluate e to the negative 800x at t? We just get e to the negative 800t. What happens when we evaluate e to the negative 800x at 0? We get 1. And so finally here, we can see that if we distribute that minus 5 out in the front, we're going to have minus 5 e to the minus 800t. And then minus 5 times negative 1, or excuse me, minus 5 volts times negative 1 is going to look like plus 5. And then we add 5 more, plus 10 volts. So we know very well how our capacitor voltage behaves. I'll give you guys a minute to write this down, and I'm going to scroll up to the top and ask what I feel is a pretty pertinent question. How does that help us? Not Ian. Any thoughts? Yeah, we know what VC of t is, and we're trying to find VS of t. So how does knowing what VC of t is help us? Let me ask you guys what I hope is an easy question. Is this Benjamin?
Since everything is in series, is the voltage drop the same across each portion?
No, right? Because everything is in series, the current flowing through all of them is the same. But that does lead us somewhere, right? You have acknowledged that all of these elements are in series, which means that we could apply Kirchhoff's voltage law and try to figure out some relationship from there. So what I mean by that specifically is, let's say I call this resistance, or excuse me, this voltage drop right here, VR of t, okay? And I call this voltage drop right here, L of t. Kirchhoff's voltage law tells us that Vs of t is simply VR of t plus VL of t plus VC of t. And you guys' suggestion, we already know what one of those things is. I would argue that the thing we figured out is actually the hardest thing to figure out. Okay? So how might we go about figuring out what VR of t is? Let's start with the easiest thing, in my opinion. Any thoughts from somebody on this side of the room? Okay, so the suggestion here by Kyle, I believe, is to apply Ohm's law because we know what the current voltage relationship for a resistor is. Capital ID, exactly what we should be doing. So we can come down here and we can say that VR of t is equal to R times IS of t. Absolutely correct, right? So that's going to be 1 kilo ohm, I believe. That's what I write it down as. Yes. Times 40e to the minus 800t milliamps. So what should that be? Yep. 40e to the minus 800t volts. Okay. Anybody got any questions about that part? Hopefully that's Alan. That is a kilo ohm. 1 kilo ohm being multiplied by milliamps gives us volts. All right. So I'm going to scroll up and I'm going to put a checkbox by this guy right here because we now know it. So how do we figure out what that inductor voltage is? Exactly right. So Jenny, I believe that was Jenny talking, says that the voltage drop over an inductor is the inductor value times the derivative of the current flowing through the inductor, which is absolutely correct. So for us, that's going to look like 1/4 of a Henry times the derivative of 40 times 10 to the minus 3 amps, e to the minus 800 t, like so. And so when I multiply that 40 milliamps times 1/4 of a Henry, what am I going to get? So 40 over 4 is giving me 10. So this is going to be 10 times 10 to the minus 3. That's a Henry times an amp. Henry times an amp. So a Henry is a volt second per amp. So we get volt seconds. And now we are taking the derivative of e to the minus 800t. So what is the derivative of e to the minus 800t? So we're going to have negative 800. And again, this guy's units is per second. So we can see that the per seconds cancel the seconds here. And so we're left with 10 millivolts times a factor of negative 800, which should give me negative 8 volts, right? So this is going to be e to the minus 800t here. And so this is going to look like negative 8 e to the minus 800t. And we know this bit right here. So we have 40 e to the minus 800t volts minus 8 e to the minus 800t volts minus 5 e to the minus 800t volts plus 10 volts. So 40 minus 5 minus 8 looks like positive 27 to me. So our answer here is 27 e to the minus 800t plus 10 volts. Kirchhoff's voltage law. Even with these nasty, gnarly circuits containing multiple different types of components, absolutely necessary to understand and apply. If I had a system similar to this where all of the elements were connected in parallel, what do you think you would use? So if you have a single node pair circuit, start with Kirchhoff's current law. If you have a single loop circuit, start with Kirchhoff's voltage law, right? All right. So I have the 40 e to the minus 800t from the resistor voltage, negative 8 e to the minus 800t from the inductor voltage, and minus 5 e to the minus 800t from the capacitor voltage. Add those together and we get 27 e to the minus 800t. All right, that's enough out of me.